Okay, so for example, let's say that front viewport, and let's do something like this. Let me take care of the others that are joining the meeting in the meanwhile. Okay, so let's say that we have a couple of points, for example, these two here, and I want to create a catenary curve. This is a way of creating a catenary curve, which is just geometry. It has nothing to do with force simulation, of course. Okay, it's just a curve. It only asks for the start point, end point, what's the length of the catenary curve, and what's the gravity direction. Okay, so by default, the gravity is set to 0, 0, -1, so it's negative vertical z-axis. That's why I switched to front view for this simulation. And then length, basically, I would calculate the distance between these 2 points and use a multiplication factor to use like something like 1 to double the length of our distance. Okay, so of course the catenary curve is a line that is hanging due to gravity. So if the length of the curve is set like equal to the distance between the point, you will only get a straight segment. So as soon as I increase this, you see that the curve starts to fall. Okay, so let's say that during a kangaroo simulation, you get this kind of deformation. Okay, because you're applying some, I don't know, some load eventually, like this, and you decide that force vector has an intensity, a module of, I don't know, -10, for example. Or you can use -1, for example, but give a weighting of 10, which is basically the same. This is something like a multiplication factor, something like an amplifier. Okay. So let's say that you have this kind of deformation. Now, the real problem is what's the meaning of 10? Okay, so that's the problem. You can work with a force vector of 10 because you have to balance the action, for example, I don't know, of any other force that you are using. So you start to mix different goals together, like loads, for example, or length line, which is elastic force for lines, for linear elements, or eventually you are working with meshes, so you have this kind of object, and you have anchor points as well. So when you mix this, each of them has a strength. Okay, so you remember that we also spoke quickly about how to find a balance between these strengths here. Okay, so the more important thing is that you don't want any force to displace, for example, the anchor points. So that's one criteria that you might want to use. So assume the strength of the anchor points is the highest by default, so it's 10,000. Okay, so say, for example, that you start to work with real elastic forces like this. Okay, so if you work with real elastic forces, these anchor points are in danger because the strength of the elastic modules here determines a very high value for the strength of the springs. And so you have to balance the anchor points. And then you have to balance also the load, because when you work with the load, if you work with real life elastic forces, you have to work with real life loads, like, for example, the weight of a structure, or I don't know, the load that you apply over a structure, and so on. So take this, like this consideration in the real world with real elastic forces and real loads, and therefore also the strength of the anchor points that has to change, and move it to a I call it a scalar simulation. Okay, so where you have just numbers, like in this case. You should have exactly the same balance between the forces, like proportional balance, in order to have a, let's say, a controlled simulation. But this is just impossible, because when you work with scalar numbers, there is actually no need to tweak, for example, each of these values in a very specific way. So, for example, how do I choose between a strength of 10 or 9? What's the meaning of that? Okay, so it's just scalar values. The only thing that you can say is that in this case, if you are working with proportional simulation, just using these scalar values for strengths, then you know that this deformation that is it's occurring in your system is somehow proportional to the real one, but you don't know exactly what's the scale factor, for example. And you also don't, not only the scale factor, what I'm saying is that you don't know exactly the balance between the strengths. So I don't know, for example, if I want to simulate a elastic cord like this one with a strength of 10, I don't know what's the, let's say, proportional value for gravity, for example. I should eventually calculate the real strength of these springs, which I can do by using the formula that we saw in the first session. And then I should, for example, let's say that this strength in the real world would be 10,000, okay? So if it will be 10,000 and I'm using 10, I know that the elastic force is 1,000 times this strength here. And so if I want to apply, for example, real gravity, which is, for example, mass multiplied by 9.81 meters per square second, then if I know the value in the real world, I should divide it by 1,000 in order to have a balance between these two things here. And therefore, I can adjust everything. The only thing that can say, let's say, unproportional are the anchor points. Because the anchor points, in the moment their strength is higher than any other strength, they work just fine because they don't move. The only goal you have with them is just don't displace during the simulation. Okay, so that might be a criteria, but it's like, I don't know. I've never done this kind of proportional determination for the strength and the force vectors. Okay, I just trust that this simulation is somehow proportional, and if I see some undesired deformation, well, eventually I start to worry about it. And another consideration, if you are thinking about, let's say, some kind of structural simulation, like, for example, beams and so on, maybe you might want to wait a few minutes and see how the beam component and the supports work, because this could be an alternative to this kind of elastic simulation for rigid structures. Okay. So remember that in this case, we are considering this is just an approximation of rigid bodies if you work with elastic forces. Okay. So I hope I made myself clear with this.
Sure.
Okay, perfect. So Ariel, Francois, Joshua, Maria, Mr. Kurz, why don't you use your real name and you you name yourself Mr. Kurz? Sounds so funny in this case. I have a list of names.
My real name. It's like I was using it with my phone, so I'll just.
Yeah. Don't worry, just joking. Okay, I think we are missing Francisco from Spain, actually, but it's just we are already 10 minutes inside the meeting. So as I told you 2 days ago, I just renewed my license for Zoom, so there is no problem of disconnection from the meeting. We can go straight to the break. The break will happen in more or less 1 hour and a half. So we will have the time to breathe some air and relax a little before continuing to the second part of this second session. In the first session, did you have the chance to watch the video? I saw on YouTube that some of you at least were watching the recording of the first session. So we made an effort to make some quick editing of it, and the upload was extremely slow. So that's why the video was available just only in the night, during the night, and not during the day. But anyway. Here
that is also perfect if you live in the other side of the world.
Yeah, exactly. So considering the time zones, I think there was no problem with the availability of these videos. But anyway, so I hope it was useful for you to have it online. So I think we are pretty all in this moment, and we can go back to our program. So yeah. Okay. Yes. Now we are all, I think. Okay. Perfect. So let's jump into this program. Let's continue from where we left. We were just considering a few examples. Remember that I just made some edits to this definition. So the yellow part is the last part of the rigid bodies, which are the beam and supports. And here the red ones are the exercises that I've been doing for these rigid bodies or 6 degree of freedom components. So you will have it, let's say, more clear in this case. And these are just 3 scenarios, 3 examples, just to see how, for example, to simulate some rigid bodies using elastic forces. Okay, so that's why we were discussing this example. I already went through the first one, so I will not repeat it. And then let's take a quick look at this second one, which is something like a bracelet. I want to simulate the interaction between the bracelet and this arm, for example. Eventually, I will just make a very quick edit to this, because it might be more interesting if we rotate, for example, this arm, let's say like the center would be 0, 0, 0. I think it's just fine, perfect. And the axis is going to be the y-axis. Sorry, let me quickly create these. The angle is measured in radians, so I will say minus p smaller than 0, smaller than 0. Okay, so this would be the angle. Okay, so if I, for example, do this, I should see, oh, it's positive because I took the positive y-axis. So if I do something like this, it should rotate. Oh yeah, okay, perfect. So I want to give some inclination to this arm in order for this bracelet to fall and stop here at the whistle. And I want to use this object here. So this is also gives me the occasion to give a quick look at other collision that are not part of the rigid bodies, like 6 degree of freedom. You see that there is a solid plane collide that we already studied and analyzed. But there are also, as I told you at the beginning, the very beginning, there is also this part here, which is only about collisions, okay? So there might be some interaction between these 2 things during a complex simulation. So what happens here? Well, basically, I just created a donut like this with a pipe and convert it into a mesh. Remember to always tend to work with meshes in Kangaroo, okay? And then I exploded this mesh and took the vertices and applied to the vertices a rigid point set goal that we analyzed as the first component in the first session, and with quite a high value for the strength, because I want this rigid point set to be like rigid, actually. Okay, so don't be affected during the simulation by any other force. So that's why I increased this value. Remember that this rigid point set establish a rigid connection or by determining the mutual distance between each pair of points. So if this distance is kept equal with a very high value, then you can assume that the rigid point set is going to behave like a rigid set of points. And then there is gravity or a load applied to each of the vertices. Remember that this is something that you might want to take into account when running complex simulation with a lot of particles or a lot of vertices, because the force vector, in this case -1, is applied to each of the points. So in this case, I have 1,500 points, more or less. So consider that this is actually one force applied to one point. If you have many points, you are applying the same load to several points. So it multiplies, okay? And then there is this one. So this is the component that I wanted to analyze. You can see that it's not in the 6 degree of freedom, it's like here. So a solid point collide. And this is very important because this is the function that allows to create collisions between non-rigid bodies also. But you can see that we are using it using a rigid point set. So these can interact both with 6 degree of freedom components and also, for example, with Gould's mesh or Gould's line if you are working with soft bodies. Okay, so it's very important to understand how it works. And exactly what you see here is that it has, well, 3 important inputs. First one are the points. So remember that what it does, you see it from the icon, by the way, you see this component actually takes a solid, consider it as a collision object, and then what it does, what this goal does, is keep all the points or the particles coming from rigid bodies or soft bodies, either outside of this solid collision object or inside of this solid collision object. Okay. Eventually, we will do some kind of simulation, like something adapting to a particular shape if we have time later on. But this is the behavior of this goal. So it requires a solid shape. You can see is the second input, which is actually our arm geometry. Okay, is this one. So this is the solid shape we want to use for the collision. And then we say that all the points belonging to our mesh, which are basically all these vertices here, are the points that are going to collide with the solid, and we want these points to stay outside from the solid. You see that there is an interior input, it's just a Boolean toggle. So if you want the points to stay inside the solid, then this must be true, interior true. If you want the points to stay outside from the solid, then this must be set to false. That's why it is set to false, because we want the bracelet to stay outside from the arm. Okay. And then there is a strength. One consideration, you see that when I work with rigid things, or with collisions, or with constraints, and so on, I tend to give these forces here, these goals, a very high values for the strength. Why do I do this? And this is a consideration that we already saw when we eventually considered applying a floor during the simulation. The floor is the same. You take the floor, and it has a strength of 1. But when you simulate some kind of constraint, like a floor, or for example, the collision with a rigid object, this collision or this other collision here with the floor, either it happens or it doesn't. You don't want a collision to happen more or less. So you don't want, for example, the points to be more or less, let's say, incapable of crossing the floor surface. Either they don't cross the floor surface, or they can cross the floor surface. Okay, so that's why I tend to increase the values for the strength, as I did here with the rigid bodies, also for the collision objects. Okay, so that's why I have this kind of high value for the strength of the solid point collide. This will help our vertices, and therefore our bracelet, to stay outside from the shape of the arm. But you will see eventually that during the simulation, this bracelet will partially sink under the skin of this arm, and then it will just jump out a little, and then just adjust to this solid object. Okay, so let's run this and see how it behaves. You see, it starts to bounce, sliding over the arm, and then it stops because there is the bristles that avoid this bracelet to move further. So this is, for example, a way we can simulate rigid bodies and rigid collision using not, for example, a solid collide. It would be also possible to do this, okay? But you can also approximate solid behavior and solid relationship also with non-6 degree of freedom components, like the solid point collide, okay? This is something that eventually is quite similar to simulating rigid bodies with elastic bodies with very high elastic modulus, okay? So we were saying at the beginning that all materials are elastic their own way. It depends on the Young's modulus they have, the elastic modulus they have. So if you take, for example, steel, with its very high value for the elastic modulus, it will produce a very extremely high strength for the elastic force, which more or less can be interpreted like a rigid body, okay? So even when we are going to simulate now the beam, you will see that the beam will be capable of bending at least, okay? There will be also other deformation occurring that we will be able to analyze, but in any case, you can consider this elastic simulation like an approximation of a rigid body simulation. So I will reset this and leave it off like this. And then the other one, I think I got some spare component here. Let me double check which is, I think it's this one. Yeah, exactly. Okay. So let me turn off everything here and let me turn on this other definition. Now this is a little more fun, I guess. It's like a game. Okay, so I was trying to simulate some kind of game where you have this body here that starts to fall and then start to collide with the walls of this, let's say, tubular tunnel. Okay, falling down. So eventually, what it does is this kind of simulation. Okay, so this is very nice because also in this case you see that we have an elastic behavior. You can see that this net is actually bouncing around due to some elastic properties. But eventually, for example, you will see that, well, let's jump and see how it was created. It's very stupid actually, but it's a way of analyzing another collision component that we have in the goals collision group. So it's basically just a circle, as you can see, converted into a boundary surface in order to populate the geometry and have this random set of points inside this circular area. Okay, and then I used the Delaunay edges in order to create this connection scheme, and then I converted all the connections into springs. And these springs, they start to have some kind of high value for the strength. Remember that this is always a scalar value in this case. Normally, when you work with real forces, this strength should be some, well, ranges from more or less 10,000 up. Okay, but in this case, I'm not using this length line. You see that it is actually disconnected from the goal objects. Why? Because I am simulating this rigid set of lines with using a rigid point set. So I took all the points, converted it into a rigid point set, so they won't be able to change their mutual distance. And I'm just using the line with a show component. If I don't do this, for example, if I deactivate this, I will only see the particles, which are the rigid points, moving around. Okay, so you see that this is the actual simulation. The lines are just geometry being transmitted to the boundary solver in order to have them available in the output of the simulation. Okay, so they are not involved. So you have this rigid body. We have a floor here. Actually, this floor is irrelevant. You see that it is disconnected. This was before I placed the solid collision that I have here, because you see that our polyline, our boundary is not touching the XY plane. Okay, so this is absolutely irrelevant in this case. But you can play around and disconnect and reconnect things to see how it works. Then there is gravity, of course, because we want this rigid point set to fall. And then there is this other solid other collision object, which is curve point collide. It's another component that it's here in this collision group, and it's very nice. It's very important because when you do something like a two-dimensional simulation like this one, then curves are basically like a cross-section of a solid body. Okay, so if you work in a plane, there is no need to work with a solid point collide. You can work with curve point collide. So that's the equivalent, okay, in 2D. And in this case, for example, you see that it works exactly the same as the solid point collide. But it has points, which was identical, and instead of having solid, it has curve. And it asks for a closed 2D curve. So it can be whatever, not necessarily a polyline. It can be a NURBS curve with a smooth aspect, okay? So you can work with whatever you want. Then you have the plane, which is in which plane you are working. And this is something that it's supported because as it is not a three-dimensional object, you want eventually to define in what plane your system is interacting, okay? So it's quite important. And then there is the interior-exterior switch. So if I set, for example, these to false, you see that our object actually is falling down because it could jump out of the polyline. If I switch it to true, this thing is going to jump back because it has to stay inside of the polyline. So this is exactly the behavior that would happen with the arm and the bracelet in the previous definition. And why, if I have a rigid point set, okay, why this object is behaving like a, let's say, elastic shape. You see that it's bouncing around. Okay, so this is due to the fact that we have a collision which has 100 strength, and we have this rigid body which has the same 100 strength. So when this body touches the wall of this polyline, the two forces are perfectly identical. So therefore, there is no, let's say, no one here is winning. There is a small amount of time in which these two objects, or these two goals, basically start to work together. And eventually, if you go at a very small scale, you might also see that this object is coming out from the wall, as you can see here, for example. Okay, you see here, and eventually also here, you see? So this depends on the balance between these two goals. So if I want this object to be more solid, more rigid than it actually is, eventually we can take this slider and increase this value to 1000, for example. So you see that now it starts to avoid its deformation. Okay, so let's say like this. But you see also that the simulation is starting to run a little more slowly. Actually, the elastic deformation is almost non-existent for this body. But on the other hand, as this force is way stronger than the rigid point, the curved point collide, this phenomenon here is not disappearing. So if we want this to disappear, we can also increase this. Let's give it the same range for now. And you see that if I increase this object starts to stay inside from the of the body. Okay. Of course, if I run the simulation right now, everything is working like a little better than before, but we have to wait several years for this simulation to complete. Now, that's why I suggest that you work proportionally. I mean, I don't care if there is some glitch, for example, in the system here, where I see that these particles are not completely inside of the body of the 2D polyline here. I don't care. I know that I'm doing the right thing here. I have created the right goals, and they are more or less proportional. So everything is working fine. I don't want to wait years for a simulation to run. So I would prefer to keep things, let's say, with a reasonable amount of strengths in order to have a quick simulation of what happens. I know that this is not an elastic body. I want it to be rigid enough. So I know that I have to tweak the values, okay? So I don't care about working with a proportional simulation. This is also valid for deformations, okay? I expect, you know, sometimes what happens is that users normally rely totally on the tool, on the software, okay? But the correct approach would be to create the simulation according to the result that you already expect to happen. So you are capable of understanding if things are going in the right direction or something is not working properly. So you don't care about the exact deformation occurring or the exact behavior of this elastic ball here, okay? Because you know what the reaction, for example, to this increment of strength, for example, for the rigid point set. You only do this if you have plenty of time to make the simulation run with its own times when you increase the strength values, okay? So I wouldn't care too much about the fact that the simulation is proportional to a real one. Okay, so these were a few examples that I wanted to show you because there is also this goals collision here, which is important. Eventually, we will use let's say this component, this function later on, eventually for some, I don't know if in tensegrity or eventually in origami. I don't know. We will see. Tensegrity actually doesn't require this because actually in tensegrity you don't have a collision at all, so it won't be necessary to work with it. Eventually with origami we might want to set some kind of particular constraints, but we will see. It's not necessarily so. Do you have any question for what we just saw, or can we move finally to our beam? You can turn on the mic if you want. Any questions at all? I see the chat here. Let's go to Beam, Ariel. Beam. Okay. So yeah. Okay. So let's turn on this. This is going to be fun. Okay. So what happens with a beam? I have prepared this, of course. Well, actually, I would suggest that initially we work with a more simple system. Yeah, eventually I would work with a more simple system. Eventually, let me do a quick tweak of this. You see that we have this, let's say, structure here. Of course, with beams, we are going to deal with architectural structure temporarily. So that's why that's what beams are for eventually. So let me just make a quick adjustment to this definition. I would work with just one beam like this. Okay, I will work with this. And of course, if I do this, I can avoid this thing here. So let me quickly take this and also this. I will explain, of course, all of these steps in a while. Okay, so don't worry if I'm doing it like without explaining right now. But okay, so this is going to be our support. Sorry, our only support. And I'm going to disconnect this. I'm doing this with the definition frozen because I'm going to tell you this as well. So let me double check. I think that everything is quite perfect right now. The frames are oriented correctly. So let's turn off everything and let's turn on everything. Yeah, exactly. So here it is, our marvelous beam. Okay, now few preliminary considerations. Okay, I kept the beam as the last goal because the beam is the more complex goal that, as far as I know, it's present here in Kangaroo. It is capable of simulating a real beam. Okay, so you will see that we will start to talk about physical properties of the beam, cross section, the inertia, and so on. Okay, and then we will be considering, for example, bending and shear strength and elastic strength and so on. So it's quite a realistic, let's say, simulation for a beam object. The only problem with the beam is that it's, I don't know, actually, my idea, my feeling is that this is some kind a function, a function that it's like if it is a work in progress. Okay, so there is something that you need to do with this simulation in order for this result to display. And what I'm using here, let's jump quickly to the end. What I'm using here is a bunch of C# scripts that I didn't make, I didn't do. These were made by Daniel itself, the author of Kangaroo. So what these scripts do is actually take the beam object that comes from the bouncy solver, okay, and decompose the beam object into several channels, as you can see. And there is the geometric channel, the momentum channel, and the torsional channel. So you have basically geometry, bending, and twisting, okay? So this is just a way of interpreting the beam output of the bouncy solver. Okay, so it's not like having, for example, a standard mesh. You see that, for example, if I take this clean tree that we have been using so far to clean the output from coming out from Kangaroo, we can take a look at this just to quickly understand what's inside this. And you see that there is no mesh. There is no geometry. There is no lines, mesh, points, none whatsoever of this. So you always see system collection, generic list, system object, okay? So it's like if this component here is actually not using the, let's say, Rhino geometric libraries, okay? It's just keep on being something like encrypted into code. So there is unique code to decrypt the information or extrapolate the information, okay? And so you have here the mesh, which is actually the representation of the beam. And then you have the bending in X and Y. And then you have the torsion. Of course, this would be visible during the deformation, okay? So the way that this simulation work is more or less like when we created well, actually, we didn't create any of this because it was part of the first, let's say, the topic was soft bodies. So it is something that was present in the webinars that I recorded previously. So if we take a line, basically, let me turn off the preview of the output, okay? We take one line, we shattered this line into segments, okay, which was eventually the same thing that we did in order to approximate, to create an elastic rope eventually. And then we create frames along these segments. Now, I'm going to explain this in a while. So you see that the geometric system is actually a sequence of segments, which is exactly like with the elastic ropes, okay, or cords. So how does this thing work? With this shader here, you define the resolution of your system. So a beam is a continuous body, of course. There is no segmentation, okay? So there is no break between one segment and the next segment inside a beam. So it's a continuous system. But as it is a continuous system, in order to analyze it, I don't know if any of you has studied structural design or something like that in architecture or engineering. But anyway, what you do is basically approximate the system, divided it into chunks, okay? So these are the chunks of the beam. And the amount of chunks is defined by the steps here. So let's leave this to 10 by default, but you can increase or decrease this amount of chunks. And this will give you a, let's say, a higher resolution or lower resolution representation of your beam, okay? So this is the approximation of a beam with a series of chunks, which actually are 10, okay? So once we have these, we created these frames here. And these frames are basically, one is at the beginning of each chunk, and one is at the end. So perpendicular frame is a component that takes a curve and creates a frame at a specific value of the parameter. You see that each segment is being reparameterized, which means it measures from 0 to 1, each of these chunks. And then when t is set to 0, you get a perpendicular frame exactly at the beginning of each chunk. So this frame here, which is highlighted right now, is the start frame of each of the chunks. So you have one here. Here is the end point of the chunks, but there is the start point of the second chunk, okay? So there is start frame, start frame, start frame. And you see that the last frame is not highlighted because it is this one. So on the other hand, we have the perpendicular frame with parameter. Yeah.
Can you explain quick what the parameter t is?
Yeah, sure. Okay, let me turn this off for a moment. Okay, I will do it like this. Okay, I will take a NURBS curve, and I will take a point container, and I will take multiple points. Like, I'm going to be very mean in this case. I'm going to take a bunch of points, and then, yeah, like this, and then many points close together, okay? So let's say we have this curve here, okay? Now, this is something that normally I explain like this to my students in order to make it extremely clear, okay? So let's say, for example, that we want to let's say, take one point along this curve, okay? And I want this point, for example, to depend somehow on the equation of the curve, not the geometry, okay? So in terms of NURBS curve, basically, this line here comes from a mathematical equation. And this mathematical equation takes into account the presence of these control points, Okay, so when you see this is something that it's quite an advanced topic um, in terms of nerves geometry. And it's explained in my book. It's quite a complex topic. Okay, so I'm going to summarize it a little. But anyway, the amount of control points that you see in a specific area determine, for example, how controlled that curve is in that area. So you see that we have a more density of control points here, less density along this part here, and more density toward the end. Okay, so it means basically that this part of the curve is at the same time controlled by a bunch of control points more or less in the same area. These affect one thing, one parameter of this curve, which is its speed or its velocity. Okay, so what happens when we want to take a point along this curve? We can take a point along this curve in two ways, two different ways: the geometric way and the parametric way. The parametric way will take into account this control point structure. The geometric way will not consider the control point structure. So the geometric way is called point on curve. So we have a curve, and we want one point along the curve. And this point, it can be automatically set to a specific value by right-clicking on point on curve and deciding I want the start point, quarter, third, mid, 2/3, 3/4, and end. So if I say I want 1/4 of a curve, this is the point that lies at 1/4 of the curve, meaning 1/4 of the length of the curve. So we are considering only the geometric aspect. So 0 means start point, 1 means end point, 0.5 means midpoint. And then there is 0.25, 0.75, and so on. Okay, so this is the geometric determination of one point along the curve. It takes into account the length of the line. And then there is the parametric evaluation of the curve, which is, for example, evaluate curve. Now, evaluate curve, in order to emit a point and other properties in that point, it needs to know what curve you want to evaluate and at which parameter. Now, what is this parameter? You might know that when you work with mathematical equations, okay, and you have some kind of graph here, you will have, for example, each of the points of this function here is determined by an x value and a y value. And normally this is what makes it possible actually to have the equation of this curve expressed like y equal something x plus or minus something constant x with a degree, I don't know, you know, there is this mathematical equation. But there is also another representation of the same curve, which is called the parametrical representation. And the parametrical representation says that during this, let's say, along this line, okay, you can express both x and y as functions of another parameter. And this parameter is normally indicated like t, okay? So x equal x of t. So t becomes the independent variable. And it also happens with y. Y is equal y of t. Now, what does it mean? It means that each of these points is determined by one single value of t, because the same t affects both the x coordinate and the y coordinate. So this is the parametrical representation of this, the same equation that we have here, okay? So t, you can see this value, that's why it's called t, as, for example, time. So as time ranges between, for example, like t equal 0, which is the starting point, in order to reach to the end point, t will simply increase its value up to a specific value, which corresponds to the end point. Now, we don't know eventually what's the value of t in the end point, okay? It depends on many things. It depends eventually on the equation of the function, of the curve, okay? But we don't know the equation of the curve of these lines because it is a third-degree equation with a differential equation. We don't want to know that, okay? I'm not going into this. You can read my book if you want. But anyway, this is the problem, okay? So one thing that eventually we don't know as Rhino users, we never take into account one thing. And that thing is this. Let me bake this curve so I have it available in Rhino, okay? We never take into account one property of the curve, which is uh, this one. Oh, sorry, not the knot vector, but the domain. So the domain of this curve is set from 0 to 19. What is this? This is the range of t, okay? But as in Rhino, this is absolutely irrelevant. Common standard Rhino user doesn't know anything about the domain of a NURBS curve, okay? But anyway, don't be confused. If I take this line and analyze the length, you see that it measures 60.121, okay? So there is no 19 here. The domain is the range of the t parameter from the start point to the end point. So in order for me to take this line and evaluate it from the start point to the end point, I should first know what's the actual domain of this line. And you see that we have here the domain output, 0 to 19, okay? But I cannot use this dynamically for the parameter definition because this curve is variable. I can take, for example, the control point and then move one, okay? And eventually I am changing things. So I have no control over this domain here. So what I need to do is give a parameter that always works, where 0, for example, corresponds to the start point, and I need a value that always will correspond to the end point. And the way to do this is to reparameterize the curve. So when you work with evaluate curve and a bunch of other components that I'm going to show you in a second, and you work with parameter here. Anytime you see parameter, what you must do is right-click on the geometry that is coming in here and reparameterize it. What does this reparameterization mean? It means that you don't care about the actual end time. You assume that your end time is 1. Okay? So you just say that the range, the domain of your line, independently from the shape, is from 0 to 1. And if you have time or t parameter set from 0 to 1, you can always define the parameter with a slider between 0 to 1. Okay? So if I do this, let me turn off these points. You see that I have another point, which is this one. T0 is the starting point. T1 is the end point. Now, what's the difference between these two evaluations here? One is point of curve, geometric evaluation, and the other one is parametric evaluation. If I set this to 0.5, you see that this point is not coincident with the midpoint. This is the physical geometrical midpoint. This is the parametrical midpoint. And it is not coincident because this point here, this evaluation, depends on the domain, not from the length. Okay, so it's a completely different way of evaluating a curve. Now, what's the use of this? Well, in our case, for example, we can work with evaluate curve. We can work with the parametric representation because we are not working with organic third-degree NURBS curves. We are working with linear segments. And the linear segments, if you take, for example, a line like this, if you take a line and use this like this, you see that both point on curve and evaluate curve with 0.5 are coincident because there is no additional control point along the way that it's basically concentrating or basically expanding time along the path. So time is constant as well as the geometric behavior is constant. Okay, so this is quite an explanation that I found out during the years that it somehow works with students. I hope it was clear. And here I'm going to also tell you what are the components that work with this. For example, the shader component itself, the shader component itself takes a curve and asks for parameters. So you might want to use your curve, reparameterize your curve, and use a bunch of parameters here to define where you're going to split this line. And of course, as you are working with parameters, for example, in this case, and we are working with an organic third-degree NURBS curve, if I take, for example, a range, which gives by default the domain 0 to 1, which is actually happens to be the exact domain of the reparameterized curve from 0 to 1, is being divided into 10 steps. So it outputs 0, 0, 1, 0, 2, 0, 3, up to 1. If I take these, okay, and this is a constant step series of values, right? The step is 0.1, but the parametric step inside this curve is not constant because this curve is lower in the area, faster here, and slower here. So these segments will not be equal. So if I take, for example, a list, well, not, sorry, I'm going to dispatch these segments, and I'm going to take a curve container like this. You see that our segments are not the same length. See? So it depends on the fact that the parameter here has a constant step, but the speed of this curve is not constant because our control points are not evenly distributed along the way. Okay? So this is not happening with a line. So if you work with a line, a straight line, you will see that our segments are just equal. Okay, so in our case, and there are also other components that work like this. One of them is the perpendicular frame. The perpendicular frames ask for a curve. In our case, it's a straight line, and it asks for a parameter. So if I take the parameter between 0 to 1, you see that here we have this behavior. Let me show the original line. Okay, so this is the original line, and we have our perpendicular frame ranging from 0 to 1. For straight lines, there is no need to reparameterize normally, because as there is no higher degree equation basically behind them, there is a linear flow along the line. Okay, so it normally, Grasshopper normally assumes that this has a 0 to 1 domain. Okay, so this is the explanation. Of course, you can reparameterize. I do recommend that eventually you always reparameterize as soon as you see parameter here. Okay, because this way you avoid mistakes with other components. Okay, but anyway, just take it like a rule. Okay, as soon as you see parameter, reparameterize the other input. This also happens with surfaces, okay? But well, I won't go through this at this moment. But anyway, I hope this made it clear. So
Absolutely.
what happened? Yeah, thank you. Okay, so basically here we have a bunch of segments. Each segment is being evaluated with parameter 0 and parameter 1. So these are all the start frame, and these are all the end frame for each of the chunks of our beam. Okay, so this is very important because if you have studied this kind of systems at university, you know that these frames here are used as the orientation for determining stresses, shear, torsion, and so on. Oh, Angelica has arrived. Okay, so I hope you have some background in this kind of simulation here, of this kind of system. If you don't, well, just trust what we are going to say right now. So these allow this component to simulate and to calculate the stresses in these connection points. Okay, and these stresses will be, let's say, taken into account as the stress that it's acting inside each of the chunks. We will see a graph coming out of this simulation here later on, and that graph depends exactly on this approximation of this segmentation of our beam. Okay, then there are basically the physical properties of our beam, and the first one, we already know this, is E, and E is Young's modulus. Okay, so we said at the beginning that all materials are elastic their own way. I just took here a value list with a couple of values, which is structural steel and reinforced concrete. So it's evident that this kind of simulation, it's useless if you are not working with some structural element, okay? So I wouldn't do this kind of simulation like to simulate an elastic rubber band, for example. It's totally useless, okay? You can do this with an elastic system or soft bodies. But if you want to work with a beam, normally users want to perform this kind of structural analysis. So first of all,
excuse Giancarlo.
yeah.
Where can I get the value list for the materials?
Well, actually, you see that this is a Young modulus expressed in gigapascal. Okay, so you might want to go, for example, on Google and look for a Young modulus table, for example. Well, you know, there are plenty of tables. Okay, plenty of tables. The important thing is that when you find this kind of values, you see there is quite a bunch of values here. It's not absolutely complete, this table. You will find more and more values if you search online. But one thing that you must take into account is that your values, in order to work with this simulation and also with my cluster that we saw in the first session, you have to look for values expressed in gigapascal, okay? Not this one, this one. So for example, you will see that you will find a Young's modulus expressed for aluminum, for example, is expressed in like 10 and 69. You need to know what's the gigapascal value, okay? And you see that there is aluminum, there is, I don't know, whatever material you might want to use. For example, carbon nanotube single walled, more than 1,000 gigapascal of elastic modulus. This is one of the more resistant materials actually available in the real world, okay? There are also others like diamond, for example. There is also graphene, which is one of the technical material that you might want to experiment with, but they are so rigid that eventually they won't even deform, or they are very difficult to deform during the simulation, okay? But anyway, you need that value. And you eventually, if you work with this definition here, you just right click on this value list, edit it, and just add the value that you want. For example, I don't know, test equal your elastic modulus in gigapascal. Okay, for example, this would be, what was it, like nanotubes. Okay, so nanotubes 1,000, and you have it available here. And when you select it, it will emit just the integer value associated to that name. But anyway.
Okay, so
yeah,
it means you can customize the component, but that component, where did it come from?
Which component? Sorry, this one.
Value list.
Value list.
Yeah,
is,
value list.
Value list is here. It's
okay.
Parameters and value list. It's a way of generating an input value from a list of values, and it's completely, let's say, you can customize it totally. So you can see, for example, when I select Ariel, I want this to emit 100. Okay, and you see that you are in the list now. So it associates a value to a name. It's a quick way to create a relationship, so you don't have to select numbers and you give a name to that values. And also with the value list, what you can do, you can create expressions, as you can see. So 2 squared minus 1 or square root of 16, you can create complex expressions if you want. Okay, but anyway, it's a standard grasshopper component. So nothing.
Now get it.
Yeah. And this Young's modulus gigapascal here is just this label here. Okay, so that's why you see this customized name. But anyway.
Okay, thank you very much.
You're welcome. So you have to know the elastic modulus, for example. So in order to work with a real material for this beam. Then you need to know, for example, what are the geometric properties of your beam. And the main properties, of course, of a beam are cross-section area. And remember, when you work with, for example, this kind of simulation, you must work with a specific unit system. Normally, it's the international system. So when you work with Pascal or gigapascal, you are considering that Pascal is the unit for pressure, for example. And if you work with this, you have to work with meters. Okay, so despite the fact that I am working here in Ranu with millimeters, I have designed a line that measures more, well, it measures actually exactly 7. So to me, this is a beam that measures 7 meters. So Grasshopper uses Rhino units in order to determine the length, for example. It doesn't care actually that 7 squares here means 7 millimeters in Rhino. It uses only the value, which is 7. So if I say that this beam measures 7, in this case, as I'm working with international system, it will be interpreted like 7 meters, okay? But my attention goes to the area definition. So the area, the dimension, base and height must be expressed in meter. So my beam is actually 50 centimeters by 1 meter, okay? So don't ever express these sliders, for example, in centimeters. Don't write here 50 by 100, because else this will be interpreted like a beam that measures 7 in length, and it measures 50 meters in width and 100 meters in height, okay? So just be aware of the fact that you must work with the international system. So here we are taking base and height. We are multiplying the base by height, considering this is a rectangular cross section. But if you don't have a rectangular cross section, you must work with this thing here in order to simulate, for example, I want a round cross section. And then you might define, for example, the round cross section by radius. And if you have it expressed by radius, you will have here a different expression, which would be radius squared by P, for example, okay? So everything is related to the shape you want to simulate. Of course, in this case, for example, the relevant part is this, Ix and Iy. So these are the second moment of area about X and the second moment of area about Y. Yeah.
Sorry. If you have a EPEC, for example, cross section, I mean, you always have to give expression, or you just write the area and the program will automatically understand. I mean, how the program can understand that it's not a square section, but is a EPEC.
It doesn't understand. You only understand the properties that you pass here. Okay, so eventually, and we will see it later on, eventually we will always get a representation of the beam like a rectangular cross section, okay? But the behavior would be the proper behavior. Because actually what you have here, for example, when you have an IP, for example, instead of a rectangular cross section, the only thing that changes are these values here, okay? So basically, for example, when you have the base, height, and then you have the thickness for the wings and the thickness for the you know, all these parameters here for the IP section, then in that case, you will have a different formula for the calculation of the area, and you will have also different formulas for the calculation of the Ix and Iy, let's say, values. So you have to prepare all these geometric aspect here, area and moments, according to the cross section that you want to use. If you want a extremely more precise simulation of a specific beam model, and then in that case, you have to switch to Caramba 3D, for example. So in that case, you can work with any cross section that you want, and it will be taken into account also as a graphical representation if you need it, okay? So remember that Kangaroo can be used like, I normally recommend to use Kangaroo as a, let's say, a preliminary study for also for a structural model, okay? So for example, I don't know, but eventually I will show you another structural example that I made a few years ago. But anyway, this is just a let's say simulation approximation of the behavior of a beam. If you want something more precise, I recommend that you switch to other plugins like Caramba 3D, for example. So
inside the parameter area, it must be an expression. You cannot just type the.
You can type if you already have the values, you can type them. Of course, you can create a panel and take whatever value here, because in the end, what this area is receiving is 0.5. So it doesn't care about the expression. The expression is something that eventually you create when you want to define the area parametrically, or the physical element parametrically. So if you want to work with a 0.5 by 1 meter, then you know that the area is going to be 0.5, but you can also change these parametrically and see how the behavior change by changing these dimensions accordingly. So the trick with parametric design or parametric tool like Grasshopper is to have access to the parametric definition, so you can change and tweak the parameters. If you don't need this, well, you can work eventually with a single panel and just type the values and substitute the values the way you need them. But for example, in this case, I could, for example, create a first group of components like this one, and let's say that I want to remove them from the group. I could also work like this. For example, I could create a number component here and copy it 3 times, and say, for example, that in case of rectangular area, okay, in case of rectangular area, I work with this. So I will name this group here like rectangular cross section. And then I might have, for example, a circular cross section. So in that case, eventually, I would define a radius parametrically, because I want, for example, the radius to be something between, I don't know, 5 centimeters up to 50 centimeters. Okay, so something like very thick eventually. And then I create an expression here, getting rid of the variable y. I just use the x variable, and then I pass the slider to this, and then I go here inside and say I want x squared multiplied by pi, and then we have the cross-section area like this. And in this case, for example, I can create another group with another output, okay, like this is the area, and then I need to calculate the ix and iy, which are not these formulas. So the advantage of doing this parametrically using these sliders here is that each time I change these values, I am changing at the same time the cross-section area and the ix and iy values, okay? So if I do the same with the circular cross-section, I will have exactly the same behavior, and I can decide what type of beam I'm going to use, okay? I will leave it like this. Of course, in this case, you have to complete with the cross-section momentum, okay? So this is the advantage of this kind of workflow. Oh, sorry, and I want to say this is round cross-section or circular cross-section, whatever you want. So basically, we are working with a rectangular cross-section. So the formulas for calculating ix and iy are these: b multiplied by h cubed, all divided by 12, and b cubed by h divided by 12. Okay, so these are formulas that you can find in whatever engineering manual or eventually online as well. So just keep in mind that you have to look for second moment, okay? Because it is not there is also the first moment, but you need the second one, okay? So what are these ix and iy? These express, for example, well, in let's give a general definition. So for example, from the perspective of these perpendicular frames, okay, so I'm going to represent this with a quick sketch. Let's represent here the perpendicular frame. The perpendicular frame has its origin in the centroid of your cross section. So if you have a cross section which is extremely regular and symmetric, okay, like this one, well, it's pretty easy to understand how it will work. But ix and iy, what they express is basically what's the distribution of material of the cross section around the y and the x axis. So these values that come out from these two expressions are capable of telling the beam component, which is actually the study of the beam dynamics, basically under stress, what's the distribution of material of the cross section referred to this perpendicular frame and to this axis. So if you have a cross section, I'm going to exaggerate, okay? If you have a cross section like this, its behavior is going to be completely different from a standard rectangular cross section, okay? And there are formulas that allow to calculate, for example, what's the behavior of this cross section referred to this y-axis and to this x-axis, okay? So that's the thing, okay? I'm going to leave it like this. I'm not going to go into engineering details, but anyway, this is what happens with this ix and iy. So basically, they are an expression of the distribution of the cross-section around the perpendicular frames, okay? So it takes into account, for example, eccentricity, asymmetry, and so on. And then there is this other module here. So this is the shear modulus in gigapascal. So what's the resistance of this specific material to basically not stretch or, well, extend or compress, which is the Young's modulus, but to shear, which is basically if you have a material or a geometry like this, well, actually, this is the direction, for example, of the beam. So you have the elastic modulus. What it takes into account is that with respect to this central axis, and this is the longitudinal axis of the beam, this object could expand and then therefore becomes longer, or it can contract, okay? So this is what the Young modulus affects, okay? Then there is the shear, and the shear makes it possible, or it's an expression of the possibility for this chunk of material to do something like this, okay? This is the definition, the graphical definition of shear, okay? So here you have a more complete representation of your material, okay? And this affects enormously the behavior, the physical behavior of this element here. And this is also what causes, for example, your element to produce some kind of torsional stress, which is something that will be output after the simulation, okay? So it's very important to have this more complete representation for this beam object. So that's why I was leaving this object for this component here for last, because as you can see, it has a more complete definition of the physical beam, okay? Of course, you can do a preliminary simulation with an elastic body, okay? But I do recommend that in the end, if you want to achieve a better result, you start playing with this beam object. And well, actually, in the end, if you have an engineering background, this is something that you might understand pretty well, okay? The problem here is that this definition, this body here, this object from Kangaroo needs some coding after, okay? I think Joshua's iPhone was kicked out, but anyway. Okay, so, okay, we're back to normal. So let's go now to the supports. Okay, now in this case, for example, the tweaking or the edit that I was doing a few minutes ago was to consider one single element for our beam object, okay? So there will be a different scenario like this, which are basically three beam objects, okay? And we are going to deal with them later on. But for now, we have one single beam, which is this one. Let me get rid of the Rhino grid, okay? So we can see, we have a better understanding of what's happening. So we have the beam here, and the perpendicular frames, which allow a discrete representation of our beam, and which define also the resolution of your system. And then there is all the physical properties and geometrical properties of your beam, okay? Then we go to the support. And supports are located, in this case, at the endpoints of our beam. So in terms of engineering, what we are simulating right now is a beam with, I hated these when I was studying, but anyway, with this kind of supports, like this, and like this. So in this moment, we are going to simulate this system. Okay, so here's the beam.
Giancarlo?
Yeah.
Hi, it's Francois.
Francois.
When you draw, my screen lags a lot. Can you just wait 2 seconds after one line, for example?
Sure. I would go a little slower. Sorry about that. Thank you for the feedback. Yeah, sorry. So what we are going to do is just this. We are going to simulate a beam, which is basically framed here with two supports that will basically avoid this extreme here and this other extreme to move in the three direction and to rotate in the three directions. Okay, so this is what we are going to simulate as supports for now. So we go here and take the first line, well, actually the line that defines the beam body, okay? And then we calculate the endpoints, and we will have 2 points. And with correspondence to the 2 points, we are going to create an XY plane. Now, this XY plane is something that it's very important to understand, because it defines what are the directions and the orientation of the x-axis, y-axis, z-axis, and also what are the rotational axes in the support point. Okay, so this XY plane is not always an XY plane. Its orientation depends on the orientation of the beam. So we are going to deal with this later on with an example, okay? But anyway, for now, as our beam is basically aligned along the x-axis, we can work with simple XY planes located at the start point and end point of the beam, okay? So what's happening where these XY planes are? Well, we place a support. And the support is a goal. Sorry, I switched to another tab here, but anyway, we are going to work with the 6 degrees of freedom, of course, and the beam is here and support is here. Okay, so support conditions you see for a beam and or rigid body. One preliminary consideration: support only work with 6 degrees of freedom components. Okay, you cannot create supports working with soft bodies. Okay, so as soon as you work with any of these components here, like rigid point set or rigid bodies or beam, then you can work with support. They will only affect these kind of objects, okay? So we are creating a support which needs to know what is the frame. So what is the orientation, okay, of the axis? Eventually, you can define a target, which is basically like when you work with anchor points in Gold's point, which is a way of defining the constraint of any system, okay? You see that you have a point and a target, okay? And the target basically tells that during the simulation, it tells the anchor point that despite its original position, during the simulation, the anchor point must move to the target position. Okay, so it's like a way of creating a displacement, controlled displacement for the anchor points. Now, in this case, we don't want to have any target frame, so we leave it let's say empty, okay? But eventually you can create a simulation where the frame or the frames are actually reaching a different position with respect to the original one, okay? And then there are simply switches, true, false. These X, Y, Z are basically movements, okay? And then X, X, Y, Y, and Z, Z are rotations. So these are the 6 degrees of freedom for any body in the real world, okay? So three displacements, 3 translations, and 3 rotations. So what we define here is X. Do you want to avoid the body to move along the X direction? True. Okay, so when this is true, it means that this constraint is on. So if I want this beam to be able to move along the X direction in the anchor point here, in the support point, then I switch this to false. But in this case, for example, if I switch X to false, it means that our beam will be capable of displacing horizontally along the x direction. There is no constraint for this beam to move along the x direction because we are affecting both anchor points, or both both the endpoints of the beam. So if you want to provide a different condition, different support condition for the two endpoints, then you must work with the start point and end point separately with two supports, okay? And you can define them individually. So each thing that you do right now in this support component will affect both the start point and end point. So I don't want this beam to move, so I keep X, Y, and Z to true. And I don't want this beam to rotate along the X, Y, and Z axis, okay? So I keep everything here set to true, and then I say strength. And I want this strength, as I told you earlier during this session, when I work with constraint or collisions or constraints in general, I always tend to give a high value, despite the fact that I am not working with real strengths. Okay, I don't care here about working with real strengths. I always work with higher values. Okay, for these constraint goals. So in this case, you see that this support here is emitting its Kangaroo solver goals support. And there are two of them because remember that we are working with both start point and end point, and we pass it to the bouncy solver. Now, that's it.
Carlo,
yeah.
That means that if you want to have a different types of support, you do it changing the rotation value and the movement value. Like example, if you want to have incastro, appoggio, you only use support component and you choose true or false.
Exactly. Exactly. We are going to simulate it soon after with this system here. Okay, so we are going to do this later on. We are going to define two different supports, for example, for the base connection point here, and different supports for the connection here between the columns, let's call it so, and the beam. Now, beam is a general, generic name, okay? With beam, you can simulate both columns and beams, okay? But anyway, we will deal with this in a while, okay? Well, eventually, after the break that we are going to have in a few minutes. But anyway, for now, let's jump to the output. Okay, so let's take a quick look at the output. Oh, and by the way, you see that in this scheme here, I am using a grab. So we discussed about the grab in the first session. It is a way of interacting with the simulation while it's running. Okay, so what I'm going to do during the simulation right now is grab one of the, I don't know, particles of a Kangaroo and move them or drag them in order to see what's the reaction of our beam object. But of course, we can work with specific loads. And in that case, if you want to work with loads, you see that in 6 degrees of freedom, you only have the definition of the geometric system. Okay, but when you want to work with loads, you always have to use, for example, in this case, I would use a load from goals point. So eventually, we will need application points for our loads, okay? But we will discuss this later on. So I have a grab which allows to drag the object drag the system during the simulation, okay? So that's how it's going to work. And you see, as I was saying, that even if we have the bouncy solver properly connected and we have the clean tree, there is no geometrical preview of the beam object because you need this part here to interpret these values that are coming out from this clean tree. Now, if you are into coding, this script is available online. Daniel shared it inside. If I'm not wrong, it is shared inside some Grasshopper discussion groups or something like that. So you can find it online, but I will share this with you. It's from him, it's not from me. So if you are into code, you might see that here there are a bunch of values coming out from this clean tree, and the amount of values that is coming out is 10. So you see that 10 corresponds to the amount of chunks that we have created with the shader and this range component. So if I increase the resolution of the beam representation, I will have more chunks coming out from this solver and coming out from this clean tree component. Okay, so here I only have the kangaroo representation of each chunk. And each chunk basically brings lots of information. Okay, so in order to interpret this information, there is this scripting part here. And what this scripting part does is, you see that this is a list of all the chunks together, 10 chunks. There is a graph here, which is basically taking each of the chunks, sending it into a different branch of this data tree. Okay, and once there is the data tree, we have basically an explosion of the content. You see, this is this is open. Okay, you can take a look at the script, what it is doing, and you see that actually this is a definition of the libraries that this script is using, but the script itself is here at the bottom, and it's very simple. It's take the list that is coming here. It means each branch, and each branch contains information about P0, P1, TX1, TX2, TY1, TY2, and twist. So it basically extrapolates the geometric definition of the chunk, the momentum of the chunks, the shear basically, and the torsion or twisting. Okay, so it's very pretty basic actually. This script is just exploding the data into several channels, which corresponds to the output. Okay, so for each chunk, you will have P0, P1, TX1, TX2, TY1, TY2, and twist. And so, therefore, you take P0 and P1 and send them to this other script. What this script does is create a mesh with other libraries. It creates a mesh starting from the points that are getting in. And you have only the initial point and the start point and the end point for each chunk, which is what happens here. And then it defines a mesh. And this mesh, it's basically located with correspondence to this start point and end point. It creates basically a rectangle around these points here using these XY values, which are the width and height of the representation. Now, one consideration, why we are not using the actual base and height of the cross section. We can do it, okay? But I'm not using, because I'm not creating a real element. I don't know exactly here the proportion between the base, height, and length of this element. In this particular case, I could do this, but I prefer to concentrate here as regards the output on the representation of the stresses, okay, not the geometric aspect. The geometric aspect is going to be this, okay? And with these sliders here, you can simply adjust the 2 dimensions of the beam. But I don't want to concentrate on the geometric aspect. I just prefer to concentrate on the stresses that I'm producing, okay? You see that you have the 10 chunks converted into 10, basically, let's say boxes, mesh boxes, okay? Which, by the way, they are empty boxes. In order to keep everything very, very extremely light. So you would see that this simulation can run in real time very, very well. So this is the geometry that we are going to use. And of course, as always, well, I don't know if you're aware, but when you work with custom preview, you can define the material here. It is just set to black in this case, so it's quite dark, but you can use whatever shader you might want. And then there is this other C# script here that takes the shear, basically, XY, X2, Y1, Y2 corresponds to TX1, TX2, TY1, TY2, okay? And represent them with another mesh representation using a scale factor, okay? So during the simulation, we will see that there would be a shear graph that comes out from each chunk, and you can decide how big that the graph is using this scale value here. And the 2 shears, X and Y, are divided into 2 separate channels, okay? So we will have, for example, these will have a shader which is red, and the Y will have a shader which is blue, okay? While our geometry has a, as a shader, which is simply this, well, it's blackish, okay? And then there is the torsion. Twist is sent to this other C# script this is quite interesting. If you want to take a look inside this create other libraries. This create an helix around the body of the beam. Okay, so twisting is represented by creating a helix. So it's a spiral, actually, not a constant helix, but anyway, a spiral is a variable radius helix. So it's the same type of curve, but it's nice to see how you can use, for example, well, actually C# is it's a little more complex. If you want to go into scripted, I would recommend that you start with Python, but anyway, this is personal. So this is the way you can create a helix or a spiral in C#. But the output is just a spiral curve, which is this green, light green line that you see here. So it only expands, or let's say increase the radius when there is some twisting occurring on this beam. So it is the green line curve. Okay. So when you work with beam, you will need this in order to visualize the behavior of the simulation, because there is no geometry coming out directly from the solver or from the clean tree in our case. Okay, so you can also turn off the preview of the clean tree. Let's run this. Okay, so this is, nothing happens here because the rigid body is properly defined, the supports are properly defined, but there is no force acting. So there is no load. Okay, so in this case, I will rely on the grab. So as soon as I grab, for example, a point of this beam, you see that our stresses are being represented with this graphic here. Okay, so you see the shear being visualized in blue and red according to the XY orientation. If I release it, due to the elastic properties, this object tends to go back to its original configuration. You see that that the graphics are slowly coming back to the original configuration. This lowliness here is due to the fact that we are working actually with real values. So structural steel has an elastic modulus of 200 and a shear modulus of 80, more or less. Of course, if well, actually, well, let's do something. Okay, so let's stop to this for the moment. Let's take a quick break, because else it's going to be very heavy to follow. And then in a, let's say 15 minutes, we will connect again and complete this discussion for the beam object. And we'll eventually, if we have time, we will start talking about tensegrity structure and tensegrity systems. Okay, do you have any questions for now?
I have a really quick one, because
yeah.
I missed the part where in the first C component in the output, the one that Daniel made.
Yeah.
You can change the size of the cross section, right? Yeah. But if you change the size of the cross section here, I mean, isn't it weird that before in the input you have one side of the cross section and then you change it here? I mean, shouldn't be the same cross section?
Yeah, I told you. Of course, you can work with the same, and actually, you simply take these two values here and plug them in the end here. You plug them in this script. By the way, if you do this, if you want to do this, and there is absolutely no problem. If you want to do this, I detected there is some kind of weird behavior because normally we consider these to be the base and this to be the height. Okay, somehow these XY are inverted. Okay, so you see that if I increase this, the height increases. Okay, so according to my personal taste, I would switch these two here. But anyway, yes, you can do this, and eventually you might simply take, for example, the base value. I'm going to drag it and plug it into the Y. Okay, and then take the Y or the height value and plug it into the X. So here is your system, okay? And there is absolutely no problem, okay? You can do this. Are you already shared it? No, today's class file will be shared at the end of this session together with the video that I am uploading later on tonight. So you can plug the real values. And here you have the system, but consider that, as I was saying, this is just a geometrical representation of the system. If you want to concentrate on stresses, then I do recommend that you decrease the values of your geometry in order to better understand the graphs that are coming out from the simulation. Okay, so that's why there is this additional input here. So if you have these, for example, and you start working with this, let's say, deformation, you see that you see nothing because the graphic is inside the body of the beam, okay? So I would recommend that you eventually, after the simulation, work with smaller geometry. Also, you can decrease this to very small values, okay? Because this will allow to understand exactly what happens in terms of stresses, okay? So that's why you have this additional definition for the geometry of your beam. Not yeah, it's weird from a let's say a realistic representation, but at the same time I understand it completely, okay? Because eventually you want to see what happens in terms of stresses more than deformation. Okay,
I agree. I was just missing that part of the explanation, and the other part that I miss is you mentioned the difference between the support and the anchor, but I didn't.
Very quickly, support are meant to work with rigid bodies. So support only work with things that are defined inside this group of components, 6 degrees of freedom, while anchor points work basically with any vertex. Okay? So you can, for example, anchor, use an anchor point to anchor a rigid point set. Yes, you can do it. Can you use a support to anchor, for example, the extremes of an elastic line? No, you can't. We were discussing here the geometric aspect. So, Tiziano, I hope everything is clear. There is no, let's say, need for us to maintain the same geometric aspect of the original cross section. But anyway, in this case, if you want to do this, I do recommend that you switch the base and height. It's not x y, it's y x actually. Or eventually, you could also, if you feel comfortable with this, each time you see x and y here, you just switch the two values. Okay, so you will have a working script using the standard order for base and height. Okay, but anyway, it's just let's say variables here. The result is the importance here is the stress. Okay, so eventually we can also turn off the preview of the geometric element in order to concentrate for a while on the stress representation, and we have the possibility to drag the elements and see how stress come out. This also allows to detect if we have some torsion. You see that torsional stress is in this case, here it is. Okay, you see it is this helix here coming out around each chunk, and the helix becomes wider and wider as the torsional stress increases. Okay, else it is just a very slight deformation, as you can see. Okay, now when this definition here is a mix, actually, the result is a mix between the simulation of Kangaroo and also this interpretation by a script. You see that, for example, if I do some change in this system, okay, like, I don't know, move around and create some stress and then stop the simulation, okay? And then you have this freeze configuration here with the stresses also. If I reset this simulation, you see that nothing happens with this graphic here. And also the deformation of the beam, if you take a look at the geometry, is not reabsorbed. So this system maintains its deformation, and also the graphic here is still displayed as if the simulation did not reset. Actually, it's not like that. The reset in this case, the only thing that it does, well, it resets the geometrical system. But as the beam, as you can see, is not by itself geometry, it's its properties. And these properties are used by this script. Then not only you have to reset the simulation, if you want to go back to the original system configuration, you must also refresh grasshopper calculation. So you can do this in two different ways. You can hit F5 on your keyboard, or you can go solution, recompute, which is basically the same as hitting F5. So if you do this, also the scripts reset eventually. So you have all the system goes back to the original configuration, and all the stresses are set to 0 in this moment. Okay. So when you work with this, there is no automatic reset. it's not enough to reset with the solver button. You will have to also recompute the simulation by hitting F5. This is just a quick note on how this complex set works. Okay. Now let's go back to our simulation. Now, first of all, there are some warning that I want to give you. You know that Kangaroo normally allows to do some edits also to the geometric system. There are some edits that you can do here in this part on the left of the solver that can be done in real time. Okay, but you don't do this with the bouncy solver or with this simulation working with this beam object. Okay, because when you get an error when working with this beam and you get some error, normally the bouncy solver will give you an error if you do some on-the-fly change to the geometric system. Then there is no possibility to recover from that error. You have to simply close the file and reopen the file. So in order to avoid the bouncy solver to get throw some errors because of the beam component, which is quite complex, I do recommend that any edit of the system you might want to do it while everything here is set to inactive. Okay. So for example, now what I want to do, I want to just change the elastic modulus and the shear modulus, which is just a number. Okay. And changing number normally doesn't affect simulation. Okay. So this is something that I can do on the fly. If I run the simulation, okay, and I change, for example, from structural steel to reinforced concrete and reinforced concrete, you see that there is no problem. Okay, so in this case, I can drag the system. You see that eventually I get a more evident deformation and a more evident graphic for these stresses, okay, which is normal because I'm using a more deformable material with respect to structural steel. And also you can see that there is more torsion. It's easier to produce torsion in this system. This is also something that eventually I have used this component recently in order to explain how stress are produced inside this beam object, because it's interesting to dynamically generate stresses and deformation and to see what stress corresponds to a specific deformation, in which point it happens, and so on. Okay, so you can also use it as a study system, this one. So you see that if you decrease the elastic modulus and the shear modulus, then in that case you will have more relevant deformation, which are both visible geometrically and from the graphic coming out from these, let's say, geometric reviews here. Okay, now if we have this kind of configuration, we can also implement some kind of load scenario. Okay, and in order to implement the load scenario, also this is something that eventually you can also try by yourself, because actually we will have a few days of break between this session and the next one, which will happen next Tuesday. So eventually, yes, I would recommend that you play around with this definition and try to implement a load scenario with the load component. Okay, this is the function that you use in order to apply a load to this beam. And as you can see, it's nice. Of course, if you want to keep the simulation, let's say, realistic, you should apply to an horizontal beam some vertical load. Okay, but you can also play around because you have a force vector that you can, let's say, determine like in any XYZ direction. Okay, and also if you work with an X direction in this case, you will tend to compress some chunks and to extend some other chunks. So let's say that you apply an horizontal X-oriented load at this point, for example, oriented like to the left. All the chunks here on the left will tend to compress, and all the chunks from this point to the right will tend to expand. Now, there is also a problem with this representation. If you orient an X load, for example, and you produce some kind of very high stress, compression stress, towards this extreme of the beam, then the simulation tends to become unstable, okay? So when you see that eventually the simulation start to, let's say, do some weird oscillation, and the graphics start to bounce around with extreme, let's say, values or extreme amplitude coming out, then you better reset the simulation and start from scratch. Okay. But anyway, it's nice for you to try to implement a load scenario. Okay. Okay, so Angelica has arrived. So for now, for this moment, I will leave this like this, and I will give it some kind of big name. I will leave it like homework. So you can do it. You can try by yourself, and we will discuss the result in the next section. Okay, so let's give an evident color like red, so you have it here available. While in our case now here, what I will do is stop the simulation, reset it, freeze all this part here. Especially, I will freeze all these beam element. I don't want to produce any change in this area. So in order to be sure, I'm going to freeze everything here. Okay, so everything that's affecting the beam and the system, it's frozen right now. Also, these two things here. And what I want to do, I want to change. I want to switch between this linear beam to this complex structure made up of two columns and one beam. Okay, so I already have everything set here at the bottom, but I will do it like from scratch. So let me remove from the group. So I will do this. Oh, it's also part of another group. So let's remove it from here, and let's remove it from here. Yeah, now you're free to go. So this is the system, okay, that we want to use. And I want to get rid also of these two things. Now, we have two columns, and we have a horizontal beam. Three different objects that must be represented by the same beam, but with different support conditions, okay? So let's say that I have, in this case, three lines. Now, it's important to understand, for example, how these lines are oriented. Because if I have this thing here, I want to create this kind of supports at the base, and I want to create some three-dimensional joint here, which allow rotations, which allows displacement in the three direction, but it doesn't allow rotational, okay? So that's what I want to do. And in order to do that, I need to clearly understand what is, for example, the start point of this vertical line and the end point of it, and the start point and the end point of it, and use the end points as the extremes, the support condition for the beam, okay? So I need to know how this system is basically oriented right now. So what I'm going to do, I'm going to take these three lines here, and you see that I have 5, 10, 5. So I already know what are the columns, which is the first and the third. And I need to know what's the orientation. So this is something that you don't do normally in Grasshopper, okay? Normally you design this in Rhino and then import it into Grasshopper in order to have a clearer workflow. So what I would do eventually in this situation, I would bake these lines in order to have them available, take them and analyze the orientation with this analyze direction of Rhino analysis, okay? So I see that both columns go from bottom to top. You see the white arrows appearing here. And the orientation of the beam is quite irrelevant in this case because it's absolutely identical if it was a symmetric configuration. The important thing is to understand what's the orientation of the columns, okay? So this allows me to understand that if I take, for example, the columns, I need only the columns. So I take, for example, a dispatch, and I will have the columns in A and the beam in B. So this is a quick way of separating the columns from the beam, because I notice that there are column, beam, column. So if I use a true-false pattern, I will have the two columns in A and the beam in B, okay? So I take endpoints, and I know that the start points are the points at the bottom. while the endpoints are the points at the top, the connection between the column and the beam. Okay, so here I have I have separated the two types of supports that I want to create. Okay, so once I have them separated like this, I take one support condition for the lower point. Sorry, before connecting this, this is something that, yeah, you can do it automatically, of course, but I wouldn't do like this, because I was saying you just a few minutes ago that it's important to understand what's the orientation of your frames. Okay, now in our case, in this particular situation here, we don't need to work with particular frames. Okay, all the frames that we are going to consider here are oriented like X, Y, and Z. Okay, so I could also connect directly the point to the frame, because you know that Grasshopper, if it asks for a frame and you only provide a point, it will use an XY plane aligned to the word XY coordinate system, and its origin will be set with corresponds to this point that you are providing. Okay, but I do prefer to do this the explicit way and create the frames because I want to see them. Okay, so these are the frames for this support, and I need to block displacement and block rotation. So I take this toggle and set it to true, because these are the lower supports, and basically copy paste it like 2, 3, 4, 5, 6. Okay, and select everything, give it an order, and plug into the displacement and rotational constraint. And the strength. Okay, so strength, you saw that I tend to work with high values, and here it is. So these are the constraint for the bottom part of this system. Now I move on to the upper part. I copy paste everything and define the same orientation for the frames. I don't need different orientation for the frames, so this will work just fine. And what I need to block here are just the rotation, because if I block, for example, the displacement, these points will not be able to move during the simulation. They will be kept in place. But I want this system to be formed globally. Okay, when I apply a load, for example, to the upper beam, I want to observe how the columns react to this load. And this is not possible if I don't allow these points to move. Okay, so I need to basically unblock the X, Y, and Z. So I will leave this to false, 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 and block the rotational movements. Okay, so these are the supports that I want to use. Okay, and what I'm going to do in order to work with this system here, which I can also, let's say, group into another possibility, another possible input. Eventually, I prefer to simplify a little this thing. Let's get rid of this group here. So the homework I'm leaving like here at the end. So we have the geometric system definition, which is this one, and the support definition, which is this one. Okay. So the first scenario was just one single beam, and one single beam we can treat it with one single support applied to both the ends. Well, of course, in this case, because we want one single support type for our linear beam. Okay. Once we go and work with with this column beam structure, I want to work with this other scenario. Okay. So what I'm going to do, and we already created this like in the rigid bodies or rigid function analysis. I can create a switch here in order to understand which goals I want to send to the solver. So the beam will always be the beam. Okay, I'm not changing anything here. We will see it in a while. So the beam and the grab will stay just the same. What I want to do is switch between this load scenario, this support scenario, and this other support scenario. Okay, so what I'm going to do, I'm going to create a data container, plug both supports to this data container, and I'm going to plug into another data container the other support condition. Okay, so these are the supports in case of one single beam and columns plus beams, okay? If I want to switch between them, I will create another data container and plug, for example, this if I want to work with one single beam. So I unplugged this directly and plug it through this switch here, okay? So this is the switch. In case I want to work with the linear beam, I connect this one. If I want to work with columns and beam, I plug this one, okay? Of course, we can do this like we did here. We can create one single data with all the goals just flowing through it. So in that case, we just need to add to each of these two the correspondent beam and the graph that we want to use. So for now, what the only thing that I am missing is basically to connect our beams and columns, which are lying here at the bottom, to this shader component here, okay? So what I'm going to do, I'm going to take this and plug it into the shader component, and let's, well, actually also in this case, I could create another switch, but anyway, we can reorganize the definition later on. Just let's have it up and running for now. And you see that now in this case, for example, this is the support definition, and this is the geometric system. The geometric system only depends on the one curve, one line's input, okay? So all the rest is just the definition of the material and geometric properties. We will leave it untouched for now. So yeah, basically that's pretty it. We just need to double check that everything works fine here in terms of data manipulation. But at this point, we can already turn on the system and turn on all this part here, and turn on also the material and geometric properties definition. You see that nothing is getting red, so there is no error detected by the Kangaroo solver because we paid attention to don't create edits in this system on the fly. Okay, so I do recommend that you take these measures in order to avoid errors, because else you will have to close everything and open the file once again. So one consideration is what happens here with the shader, because now it is receiving 3 lines. Each of these lines is being shadowed into 10 segments, okay? So we get a data tree here with 10 segments per branch. And so these perpendicular frames are being created in all the 3 branches, okay? Which is perfect for us, okay? Because we need this representation for all the 3 elements. And the start frame and end frame, they don't specify whether they need, for example, lists or trees or data trees and so on. So when you see these, it's more likely that you can work with data tree without any problem, okay? And after all, in this particular situation, we are not considering that the columns are different from the beam, okay? We might want to consider, for example, concrete columns and steel or metallic beam. In that case, we should be, let's say, splitting the problem, creating 2 beam objects, one for the columns and one for the beam, and then sending not all the 3 lines with one single output here, but specifying the properties for one beam type and another beam type. And of course, this means also specifying a different Young modulus, shear modulus, and all the properties of the cross-section and inertias for these cross sections. Okay, but in this case, we are considering one single material and one single cross section for our beam system. Okay, so when we run this, now we have one single system. If I drag this, you see that I am affecting also the columns. Okay, and this is because I have a joint here that allows displacement of this joint, but not rotation, okay? So for example, the beam cannot rotate with respect to the columns, not here and nor in the other end, but these extremes can move. So you see that this is the kind of deformation that we get from this action. Of course, this also works if I drag this column, because this is also part of the whole system. And you see that, for example, torsional stress starts to appear. But in any way, this is something that now we are doing like on the fly, like dragging the system around in order to see how it bounces, how it reacts, and how the stress starts to appear and disappear. But I do recommend that you do this using fixed loads. Okay, so with fixed loads, you can see how the system reacts. For example, if I apply loads in the center part of this system, like for example, well, actually, this could be also part of the homework if you like. For example, you can create the very exact system. So don't focus on changing materials and so on if you don't feel like you want to go that deep into the simulation. So create this kind of simulation here where you basically leave all the supports untouched and you concentrate only on the load definition. So I want you to apply, for example, a load only in this area, like this. Let me take a while to write it down clearly. So I want you to apply a distributed linear load along the upper beam, not reaching the extremes, okay? Just stay in the inner part of the beam. And what should happen during the simulation is that you should see that basically this beam starts to deform like this. And also the beam, the deformation starts to, let's say, as it has quite a strong Young modulus, there should be no relevant, let's say, longitudinal deformation. So the global length of the beam should stay more or less the same. It means that if it bends like this point should move towards the center of the beam, but also should move down a little because of the load that we have applied. And also, as there is no possibility for this vertex here to allow rotation, it can only move, then this movement that you have should also create some kind of deformation like this for your columns. Okay, so this is the result that you might want to observe during the simulation. Now, that's why I was saying that when you conduct some simulation with Kangaroo, even if you want to work with, let's say, soft bodies or extremely rigid elastic system, okay, like created with length line, for example, it's important that you have a general idea of what type of deformation, what type of result you expect for your simulation. Okay, then in that case, it's easy to understand that the real life scenario is probably not going to be this kind of deformation. And in a real structure you have this kind of deformation, you start running away because it's going to collapse in seconds. Okay, so you know that it's not going to be like that. It's just this deformation, but with a scale factor, basically a proportional factor. Okay, so you have to think about this result as a general deformation that you get. So let me add this to this group. So this is what you are going to do as a homework. I like giving homework to the students. Yeah.
A question about loads.
Yeah.
If you want to simulate, I mean, uniform load or point load, because the component that we are there in the screen, if I understand correctly, is point load.
Yeah.
But if I want to have a uniform distribution, is it enough? I mean, because if you divide the line in 10 parts and you said that the point load is that, it's not really a uniform distribution, but maybe there is another component to say instead of 10 points is all the line or all the surface that
and I'm going to tell you why. Okay, I understand clearly your question, but I was saying that the quality of this simulation depends in the end from the resolution that you give to the shader, basically, into how many chunks you want to divide your elements. Okay, now the amount of chunks will not affect the general behavior, because when you work with real life forces or real life let's say modulus like this, the global deformation in the end, does not depend on how many chunks you are considering, okay? Because the stresses and forces that are being considered right now are very strong, okay? So the global deformation is not affected in a relevant way from the resolution that you decide to work with here, okay? Now, this resolution, you can increase it in order to have a more continuous representation of the system. The problem is that mathematically, like when you study, for example, engineering, you have formulas that allow to consider, for example, in static problems, what happens when I apply a continuous linear load to a linear element like this one. But in order to reach to that formulas, you do some kind of calculus operations, okay? If you want to use a computer, okay, and you say, well, I want to apply a linear load to these horizontal elements, and the simulation is based on this mechanism here, which is basically a discretization of the problem, okay? So if you want to consider a linear load applied to each element, to each fiber of this linear element, how many fibers would you be considering? Eventually, this amount becomes infinite, and you cannot ask a computer to perform infinite amount of calculation, okay? So you always deal here with a finite number of elements. And each element will receive a specific load, which is proportional to the linear load. So for example, the only consideration that you must do here when you define, for example, this load that will be applied, specifically, it will be applied at the end point of these segments here. So you will need to evaluate this curve, for example. Oops, sorry, my bad. I have to evaluate the initial lines like this, reparameterize them. Remember that anytime we see parameter, we reparameterize the geometry, and then we use as a parameter the very same range that we have used for shattering. So in this case, you see, for example, that we start to see the points. Let me stop the simulation in order to avoid any risk, and let me also turn off the preview. And in this case, for example, you see that while shatter works in the proper way, because shatter itself, it's the function, or let's say, you know that inside this component there is a script, right? There is code. And the code inside this component, it's using the list of lines separately. So it takes the first line and divides it into 10 chunks. Then takes the second line and divides it into 10 chunks, and so on, okay? While evaluate curve doesn't work like that. Evaluate curve is receiving 3 lines and 11 values for the parameter. And it is using a longest list method in Grasshopper, which says this first value here interacts with the first value here. So the first curve is being evaluated at parameter 0. The second curve is being evaluated at parameter 0.1. That's why you see the first line is this one. You have this start point here, which is point with parameter 0. The second line was this one. It is being evaluated at parameter 0.1. That's why you see this point here. And the third line is being evaluated with parameters from the third value, which is 0.2, down to value number 1. Value 1, sorry. So you see that all the remaining division points are here. So first line receives only the first point, the start point. Second line receives this point here, which is not the start point, it's the second evaluation point. And the third line receives all the remaining evaluation points. We don't want this, because eventually we want to apply the load only to the horizontal beam, okay? And so in order to evaluate this curve and apply a load, which will do you will do like here, for example, we have to take the lines and eventually dispatch them as we did before. Take the least beam, which is the only beam that we have, and now we will have one single beam evaluated with all these 11 parameters here. And so we have the 11 points. Within these points, we need to delete the first one and the last one. And we want to apply the load only to the inner point. And eventually here, I would use a call index, because it's the easiest way to eliminate points from this set here, because you know that if we have this list of points, in order to eliminate the first and the last, you have to provide index number 0 and index that corresponds to the amount of steps that you have in this range, which is the amount of chunks that you are getting. Okay, so if we parameterize steps with a slider like an 11 slider, set it to 10 because actually it is set to 10. We can use, for example, in order to call index, we can use number 0 because it is the first index that we want to delete. And we can use the slider here connected also into the index component. So you see that call index is actually giving us only the inner point. And here we can apply the load. Okay, so it's just a bunch of data manipulation steps here in order to get rid of the useless values or data. And then finally applying the load to this call index. And I will share this definition with you, so you don't have to repeat this, but I want you to play around with this load here, additional load that we are applying, okay? And also to realize, as we are working with real strengths here or real modulus, for example, what values produce an effect when you use the load? Because consider that actually the load has a force vector of 1. So it is an intensity of 1. It is orientated upwards, so it's not let's say, real-world vertical load. It must be oriented downwards, so you have to tweak the value here. And you have to use the proper module for this force vector, because else it won't produce any deformation in the system, okay? So yeah, play around with this and let's see what happens, okay? I encourage you to experiment with this simulation because it is very, very nice to work with it. So yeah, in the end, I will leave it like here for now. I will group these like part of the homework with the same color, so you can recognize that they are somehow part of the same exercise, okay? Actually, you can do this, I don't know, this is just for relaxing a little, but if I select these and these, I can group them all together and change the shape of the group from a box outline to blob outline, for example. Or if I want to be more, let's say, rational, I can use a rectangle outline like this. And if I change the color to this, I will be changing the color to the whole group, so everything is connected, okay? So you have a clearer understanding of what are the elements involved in your homework. Okay, so this is our new simulation, as you can see, and remember, everything works properly right now because we didn't have to take into account different orientation for the structure. And eventually, exactly, the last thing that I want to show you is what happens when you have different orientations for your beams, for example, or structure in general, okay? So let's, I will take all of these things. It has become quite chaotic. Eventually, I will rearrange a little this initial part here for the geometric system so that you will have a switch, also a general switch, so you can switch between the linear beam and the complete structure like this. But anyway, for now, I'm going to, well, actually, I'm going to take the beam with modulus and also the geometric cross-section definition here. And I'm going also to consider like this first part here. So the simple system. I'm not going to work with the complex structure, okay? Just the simple system. And also, eventually, I will take all the rest here and I will freeze everything, copy paste it, move it down here, and have it already available. Now, the only thing that I missed here was the switch, but I don't need a switch in this case. So I'm only going to work with, let's unplug the support condition. And also, I also miss a grab. So I'm going to disconnect the grab here. And I'm going to reconnect the supports and use another grab object and plug it into the solver. Okay, so what I'm doing here is just going back to the linear beam. Okay, no rocket science. So let me readjust this cross section just in order to have it clearer. Yep, that's pretty it. So let's see, for example, what happens when we have a different orientation for our beam. Okay, so I'm going to turn everything off here and group it so we have it available later on in order for adjusting things before sharing this second definition with you. Okay, so let's say we have this beam here. Now, strategically, this beam was oriented like the x-axis. Okay, but it's not. The fact is not that it is oriented as an axis from the coordinate system. Because even if I change, for example, the orientation of this beam and I place it along the y-axis, we can no longer work with the actual support, okay? Because things will tend to work in a weird way. So what I would recommend in this case is this. Let's say that we want to work with a generic beam like this. This is not aligned with any of the axes from the coordinate system, okay? So what we must do in this case is not enough to, for example, take the endpoints and create an XY plane, because the XY plane is actually aligned with the XY global coordinate system. And eventually, we want to avoid, for example, to us, X movement should represent the X movement along the line of the beam, the longitudinal axis of the beam, okay? Now, this is not mandatory, okay? This is something that, for example, if you want to frame this and just avoid any type of movement in any of the 6 degrees of freedom, then there is no particular reason for changing the orientation of the XY plane. In the end, nothing is moving and nothing is rotating. Okay, but if you take this frame, for example, and consider, for example, the X rotation, okay, the XX. Now, XX in this case doesn't mean a torsional rotation, a twisting. It means that in this point, what's not allowed is rotating along this X direction, which is something that has basically almost nothing to do with the geometry or the orientation of your system, okay? So what I would recommend in this case is this. You take the endpoints, okay, of this line and use them in order to create a frame which is aligned with your beam. How can you do that? Well, there are several things that you can do. But first of all, you can take an evaluate curve, plug this line here, reparameterize it, take as a parameter, for example, a slider between 0 and 1, and plug it here, okay? So let's get rid for a second of the XY plane. You see that we have our point. We already know that if we slide this from 0 to 1, we have intermediate points, but we only need 0 and 1. So let's consider 0 for now. And what you have from evaluate curve is the point, but also the tangent, okay? So if you have tangent, which is a vector, you can also take a look at this by using a vector display and showing this vector anchored to this evaluation point. So you see that we get the vector here, which represents the direction of the line in the point that we are evaluating, okay? So you see here, well, let's take the end point. So it's clear there is no overlapping between the vector and the line, okay? So we are working with the end points in this moment. So if you have the tangent vector, you can also you can also use it to construct a plane oriented exactly like you want. So for example, let's do it like in a very explicit way, okay? So it's a very step-by-step construction. You can rotate, for example, the vector. There is a rotate vector, which is not the standard rotate. You can find it into the vector toolbar, and there is the vector group of component, and here is the rotate vector, Okay, so it asks for the vector you want to rotate, and it asks for the axis of rotation, which is in this case is z-axis. You see the axis is asking for a vector, so we provide a vertical vector, and the angle. The angle is 90 degrees. What I'm going to do, I'm going to rotate this vector 90 degrees counterclockwise, which is positive rotation, in order to have the y-axis. Okay, so here, remember that in Grasshopper angles are measured in radians. So if you are comfortable with radians, you know that these should be p divided by 2, which is 90 degrees. Okay, and if you do this, you will see that we have this vector right now. Okay, so now we have the x vector and the y vector, both of them. So we can use, for example, vector, plane, and construct plane, and say we want a plane which has the origin in this point here. The x-axis is the tangent, and the y-axis is this vector here. So we already have a frame which is perfectly aligned with our beam, the x-axis being the longitudinal axis of the beam, y-axis is the cross direction, and the z-axis is oriented vertically upward as it should be. This depends on the fact that we rotated the vector properly 90 degrees counterclockwise. Okay, so here's the way of creating this frame, and you can also work, for example, with a couple of sliders and plug, for example, 0 first and 1 second. So we have, despite the visualization, which is absolutely irrelevant to us, what we need is just the 2 frames. As you can see, now we have the frames properly aligned with the beam. And from now on, everything goes back to normal, because we can plug eventually this construct plane here instead of the XY plane to the frame of the support. Okay, so here it is. And this is a more general definition that you might want to use instead of the endpoints plus the XY plane. So these work with any orientation for our beam. Okay, because if you change right now, if I take this and change set one line to this one, you see that the frames are oriented accordingly. Okay, so if you want to work with a structure or the orientation not aligned with the XY plane or axis, then you might want to work with this kind of definition. The orientation doesn't affect the geometry of the beam, okay? Because in the end, it's just chunks and eventually application points for the loads, okay? So it's just geometry, it's not orientation. So there is no need here to change things. And the rest is numbers. So even in this case, there is no need for changing anything. The only thing is when you define the support, always pay attention to the orientation of the frames, because this will affect the meaning of X, Y, Z, and X, X, Y, Y, and Z, Z. Not locally. Locally, everything will always work just fine as regards the support, but the meaning of this must be, let's say it must be meaningful with respect to the orientation of the beam, okay? Not with the effect of the constraint themselves. Okay, so everything must be set up properly in terms of geometry and in terms of supports. So in this case, for example, we will have the proper behavior. Everything will work just usual, as you know, as we already tried with the linear beam. So there is absolutely nothing else to do in this definition, but this little change as regards the definition of the frames for the support. Okay. We still have 5 minutes, and I understand that this topic here it's a little more complex than the standard Kangaroo, let's say, goals and structures and the topics. So I would like to ask you if you have any questions or something that you want to further discuss, or you tell me. I think you all fainted out.
Hi. For example, this can be applied to a laminar structure, like one made of a hyperbolic paraboloid.
Whoa, Hypothetically speaking, you can simulate whatever type of structure you want. Problem is that the system starts to be quite complex, and the simulation also starts to be quite complex. Well, let's put it this way, okay? You can, as I was saying to Tiziano a few minutes ago, you know, in real life you work with continuous systems, okay? So, for example, a beam is a continuous system, but here, for example, we must do some kind of discretization of the system because we cannot work with an infinite amount of points. So, in this case, for example, for a linear beam, we use the shader component. So, in terms of a laminar body, for example, let's say you want to simulate a square surface, for example. In that case, you have to, let's say, approximate that body there in two different ways. You can do this in two different ways. First of all, you can use a soft body because the soft body gives you the quickest representation for a two-dimensional object, okay? So we didn't discuss this because it is basically part of the elastic section, let's say elastic part of a Kangaroo course, okay? It is something that we saw in the webinar that was recorded, okay? But in general, what you have, for example, for a soft body representation, normally you can define whatever surface you want, like this one, and then use a mesh surface in order to create a mesh representation of this surface. The advantage in this case is that you have access to the edges, okay? And you can convert this mesh surface into an elastic body, exactly with this shape, and this amount of longitudinal and cross beams, let's call them so, okay? So yes, you can do this, and the quickest way is to approximate this with a mesh surface and use, in that case, for example, the standard elastic workflow, which is what you get inside your Gold's mesh, okay? But in that case, we already saw that you have to work with real life strengths. And in case of the beams, you have it straight. These values are directly connected to the E. And you also can consider, for example, the shear modulus, which is something that you cannot consider in this kind of approximation with a mesh, okay? So this is the quickest way, but it's quite a rough approximation. If you want to work with real beams, which is something that gives you a more realistic behavior, then you must create each line of this net should be converted into a beam. Okay, so the simulation starts to be quite complex in terms of definition of the system, but in the end, the only problem with Kangaroo is creating the geometrical system, and you give all the properties that you want to that system. We will see, for example, with the tensegrity, I will share with you one example that has a very complex tensegrity structure. So the problem in that case was not programming the tensegrity behavior, but was drawing the lines of the poles and of the elastic chords of the tensegrity system. So basically, it's not like, is it possible or not? Of course, it is possible, but you have to understand what elements will be converted into beams or into elastic nets or whatever type of geometry you might want to use. Okay, Angelica?
Yes, thanks.
You're welcome. So, for example, there was this client from India that was asking, I want to work with a, let's say, a bamboo structure, for example. How can I simulate bamboo structure in Kangaroo? Is it possible? Yes, it is. Of course, I repeat, this is just a preliminary analysis, okay? I will not rely on Kangaroo 100% for a real simulation, okay? I would eventually integrate, for example, Caramba 3D, which gives a more realistic simulation in that case. And also it is capable of considering much more properties, both in terms of geometric aspects, that then also for the stresses and so on. Okay, so in any case, I will not rely 100% on Kangaroo, but yes, you can simulate also, for example, bamboo structures in Kangaroo. Just define the elements, the structural elements properly, and just use, for example, the proper Young's modulus, for example, and shear modulus if you're working with beams, or just realistic strengths if you're working with a mesh edge length. Okay, so yes, you can do it. Any other question?
Yeah,
Ariel.
me.
Yeah.
What do you think it's better for simulate Kangaroo or better analysis plugin like Caramba?
Well, yeah, it depends. Okay, so as I told you, for example, when we worked um, on the dome of the Sport Palace of Mexico City, the problem in that case we had was to simulate a tensegrity structure for the dome, and then perform accurate calculation, okay, for the deformations occurring on this structure. So the first part was solved by using a standard Kangaroo approach, creating a huge tensegrity structure. Eventually, I can show you the file in the next session when we will be working with tensegrity systems. And then the second part was Caramba 3D. So it's not either one or the other. You can work with both of them. Okay, so I don't know. Probably in a professional environment, I would integrate the two of them because they provide different information for the system. And eventually, I repeat, the reason why we started with Kangaroo and then we used Caramba to refine the simulation is because with Kangaroo we were conducting some preliminary study in order to first understand if a tensegrity structure would eventually work for that kind of shape. And you don't need to execute precise calculations in that case. You just want to understand if the dome collapses or not. And you can do it with, let's say, in case of strengths, you can do it with scalar strengths. There is no need to consider real values, okay? So we just work with, in that case, with linear springs like this. And we work with scalar values like the original 10 strength for the springs. There was no need to provide real stresses and to understand real deformations, okay? And then we switched to Caramba 3D in order to understand, okay, so let's see what happens if we work with real stresses and real forces to this structure in case it was a tensegrity structure. So in that case, for example, we measured exactly what was the displacement of the dome, let's say, well, not falling, of course, but deforming according to the real weight of the structure, okay? And we saw what was the deformation using Caramba 3D, because it is more precise, because it takes into account with more detail all the stresses occurring into the structure, into the structural elements, and also the calculation of the deformation is more realistic, okay? So it is not either one or the other, it's both of them.
Okay, so Kangaroo is good for the first approach.
Yeah, I would say so. I would say so.
Okay, so thank you.
You're welcome. Okay, guys, any other quick questions? Or we can just look forward for the next session, which is going to happen next Tuesday. If you have any doubts or something, if you are going to play with this definition that I'm going to share with you along with the video later on today, I do recommend that you do this. I do recommend that you play with these scripts. If you have any questions or any doubts or you don't remember something, etc., there will be the video uploaded. But if you have any particular question, just drop me a line, and eventually I will answer. Either I will answer, or I will tell you we will discuss this together with the rest of the group, because eventually it is something important for everyone. Tiziano, tell me.
Maybe it's not really related to what we have discussed today, but I think that interests me a lot regarding structure is the structure that is connected with the form, following the form, and also the thickness. A lot of architects like Nervi, Candela, and other among, they were working a lot trying to use the minimum material in their structure, and also using a shape that reply to the structural principle.
Mm-hmm.
Will it be possible to do some easy application with Kangaroo? And if yes, will we discuss about some components that can help us to manipulate structural forms and parameterize them in a way that you can see what is the best form that respond to. No, okay.
No, and let me tell you why. The approach that we are having right now is different. Okay, so let's consider, for example, the thing that we have not discussed, and we are not going to discuss in this course, are the soft bodies. Okay, so like elastic bodies. Okay, we are focusing on rigid bodies. Now, when you work with rigid bodies, the shape is already defined. Okay, so there is no need to let's say optimize the shape. While if you work with soft bodies, for example, it's like, well, you were talking about Candela but if you think about, for example, the work from Gaudí, okay, or Fray Otto, for example. So in that case, the approach was exactly the opposite. You don't have any shape. You just have some spatial need, and you have an idea of the loads that are playing a role in your system, and then you let the system take the optimal shape. This is something that happens with soft bodies. Okay, so this is something that happens, for example, with catenary curves. If Gaudí had access to Kangaroo, it probably would have been the happiest man in the world. Okay, so in that case, there is some optimization occurring in naturally in the use of Kangaroo. Okay, but it's just because the system takes its equilibrium shape according to the loads and to the restraints that you are providing. Okay. But what you're talking about, the optimization, for example, in terms of the amount of material, just keep the structure as light as possible. This is something that has to do with a different theory, which is called topological optimization. Okay, and if you want to explore it, what you can do is start playing around with. Yeah, exactly. This one, Topos. Topos it's quite a nice plugin. Once there was this other one, which was called Millipede, which is this one. I think Millipede was pretty amazing, but unfortunately, somehow it's discontinued, because if you go into their website, you see that it's stuck to, I think it was 2014 or something like that, more or less. It's still valid. You see, I still have it installed. I still use it for some application, but recently I've moved to Topos because Topos also has another feature which is quite interesting. It doesn't work only with box objects. Okay, Millipede only can work with boxes. Okay, both in volume definition and so on. While in Topos you can work with freeform shapes and see how, for example, to optimize the topology of that freeform shape. So I do recommend that you take a look at Topos. There are also, let's say, each of these plugins here, which start to be quite complex, come with a set of examples, okay, example files. So you can easily understand, if you have an idea of what is topological optimization, you can easily understand how it works. But yes, eventually not with Kangaroo, not even with Caramba 3D. I will do this with Topos in this case, in this moment. Tomorrow, I don't know, maybe another plugin will come up with which is more effective. I don't know. For now, I prefer to work with Topos.